Welcome to this short video which introduces the workings of a completely new propulsion technology. Known as oscillating counter-rotation or super oscillation, this technology decisively outperforms currently available technologies in thrust produced per unit input of horsepower. The system is based upon the contrapel counter-rotating drive. In this video, we'll begin with a brief outline of this system. The interested viewer, however, may like to review the contents of the website at www.contrapel.com, since the workings of the non-oscillating drive are outlined in much greater detail here. As the phrase counter-rotating drive suggests, the system is built around counter-rotating hybrid propellers. The technology can operate above or below the waterline. For the purposes of this video, the bow of the vessel can be visualized towards the left of the screen, and the water can be visualized flowing across the screen from left to right. The black propeller to the left of the screen will therefore be known as the upstream propeller, while the blue propeller to the right will be known as the downstream propeller. Looking from upstream to downstream, it can be seen that the upstream black propeller on the model turns in a clockwise direction, and the blue downstream propeller turns counterclockwise. The diagrams have been simplified as far as possible with the removal of all unnecessary visual elements such as intake ducts and so on. To state it very simply, the contrapel drive functions by imparting radial energy onto the fluid mass flow with the upstream propeller and then removing it again with the downstream propeller. This provides a plume without radial energy which creates thrust in an above the waterline propulsor. In order to understand how this works, it is important not to equate the system too closely with a pressure jet, even though it outwardly resembles one. As a non-compressible propulsive medium accelerates through any propulsion system, its cross-sectional area decreases. This is true of any mass flow of non-compressible fluid that accelerates between 2 points and is known as the continuity of mass flow. The traditional water jet brings about this acceleration by manipulation of cross-sectional area in conjunction with pressure. The fundamental insight required to understand how the contrapel system works is that there is another way of doing this. This is immediately understandable when one considers the water falling from a tap faucet. As it falls under the influence of gravity, it accelerates and its cross-sectional area decreases. The insight is that if the mass flow is already changing its velocity by an alternate means, its cross-sectional area will change as a result without any direct manipulation of this parameter. The acceleration of water occurs over the contrapel blades, which is the source of the thrust, in similar fashion to the standard propeller that we are all familiar with. The cross-sectional area it assumes downstream is a simple byproduct of this velocity change. For this reason, neither downstream cross-sectional area manipulation nor pressure are required to perform this particular function. It is also why the contrapel blades are termed hybrid propellers and not impellers. The next section of this video outlines the functioning of this system with the addition of a rhythmic oscillation, hence the name oscillating counter-rotation. The particular example demonstrated here is of an oscillation in the vertical plane. The effects of the oscillation begin at a very low proportion of oscillation amplitude in relation to the propeller diameter. In order to visualize what is happening, a large amplitude oscillation has been used here. What is immediately apparent is that whereas the blade tip trajectories of all points on the non-oscillating blades follow a simple circle, the blade trajectories of the oscillating blade points become highly diverse. For example, if we remove two of the blades for clarity, notice that the indicated point follows a long elongated path. Now look at the downstream end of the same blade. Its path is entirely different. Virtually all its vertical motion with this particular oscillation form and amplitude has been cancelled out. In contrast, the other blade behaves in the opposite fashion. The upstream tip follows a flat trajectory while the downstream end becomes elongated. A gradual transition between these extremes occurs as you move along the blade. The reason for this transition results from the particular point on the compass a given point on the blade starts in relation to the oscillation. In the case of the extreme elongated path, the direction of the vertical component of the propeller rotation is always the same as that of the oscillation. In the case of the flattened path, the direction of the vertical component of the propeller rotation practically always opposes and cancels out that of the oscillation. Adjacent blades behave in a similar fashion except that they are altered in phase according to the relationship between the blade's compass start points and the oscillation. All this is highly significant since the interaction between the medium and the blade changes as the medium moves along it. Not only that, the downstream propeller oscillation maintains precise alignment while turning in the opposite direction. It is therefore perfectly placed to interact with the force and velocity inputs of the upstream oscillating propeller. What results is an extremely effective interplay between the blades and the medium which they act upon. Of course, with lesser degrees of oscillation, this effect is far less visually apparent. The effect that it has on the performance of the unit, however, is entirely unmistakable. Before we go any further, we need to establish a basis for comparison between the motion in space of the oscillating and non-oscillating blade points. For this reason, we will now introduce the concept of theoretical pitch. Theoretical pitch is defined as the linear distance that a propeller would move in one complete revolution through a solid, not allowing for slip. The pitch of the blades shown is made up of a radial and an axial component. When turning, the radial component of the blade pitch just downstream of the dot is continuously moving out from the page and down, so that when moving along the rotating blade, only the axial component of the movement is visible in the motion of the dot. For the particular 45-degree pitch propeller shown, the dot moves along the axial length of the propeller once in every half revolution. The distance it moves in a full revolution, i.e. the theoretical pitch, is therefore equal to 2 times the axial length of the propeller. The downstream propeller can now be included. Remember, the upstream and downstream propellers turn in opposite directions, and in this example both have the same pitch and turn at the same rate, and so the depiction of the theoretical pitch is therefore continuous from one propeller to the next. So what happens once the oscillation is introduced? The dots moving along the oscillating model are simply the equivalent points which occur on the non-oscillating model, but with the oscillation factored in. We will call this the oscillating pitch. There are 3 basic categories of interaction between the blade rotation and the oscillation in the lateral plane indicated by the green, red and blue dots. Where the direction of the vertical component of the blade rotation is the same as that of the oscillation, it is represented by the green dots. We'll call this additive oscillation. Where the direction of the oscillation and that of the vertical component of the blade rotation oppose one another, we will call this subtractive oscillation, shown in red. And thirdly, at the top and bottom of each oscillation, the motion imparted by the oscillation is 0 for an extremely brief period of time as the direction of oscillation changes. Represented by a brief flash of blue, we will call this 0-point oscillation. Notice the symmetry of the system. Whenever additive oscillation is occurring on the near side of the upstream blade, a proportional subtractive oscillation is occurring at the equivalent point on the near side of the downstream blade. This switches back and forth. This occurs because the direction of movement provided by the oscillation component is always the same between the upstream and downstream propellers. And when it changes direction, it does so at the same time for both, while in contrast, the vertical component of movement resulting from the rotation of the upstream and downstream propellers is always in opposition. For example, the vertical component of the rotational motion provided by the near side of the upstream propeller in the indicated area is always moving down, while the vertical component of rotation imparted by the near side of the downstream propeller is always moving up. Notice too that whenever additive or subtractive oscillation is occurring on the far side of a given propeller, let's say the upstream propeller, the opposite form of oscillation is simultaneously occurring on the near side of the same propeller, while the near side of the downstream propeller is undergoing the same form of oscillation as the far side. These also switch rhythmically back and forth. All this switching occurs as the oscillation moves through its top or bottommost points and then changes direction. As the oscillation approaches one of these points, the vertical motion it provides will slow, briefly stop, and then begin to accelerate once again in the other direction. This simultaneously causes the velocity of any additive oscillation to slow until it reaches 0-point oscillation, while the corresponding vertical velocity of the other propeller will increase as the level of opposition between the vertical velocities of the oscillation and blade rotation slowly tail off to 0-point. The two propellers at this instant have identical vertical speeds, but oriented in opposing directions. The additive and subtractive oscillations then reverse as the oscillation once again begins to accelerate in the other direction. What results is a very gradual and smooth transition in the relative vertical velocities between the upstream and downstream blades, which corresponds with a smooth rhythmical transition in the force vectors transmitted into the propulsive medium. It is tempting to view additive oscillation as adding to the system, with subtractive oscillation removing, leaving zero net gain. But this is not the case. The addition of the oscillation alters the application of force and velocity vectors to the propulsive medium in such a way that the effects of friction appear to be reduced, causing the medium to accelerate through the system to a higher final velocity for a given input of horsepower than previously thought possible. While additive oscillation is adding force and velocity vectors to the medium, for example via the near side upstream blades, subtractive oscillation on the downstream blades simultaneously renders them streamlined to receive these vectors. As 0-point oscillation is approached, the force and velocity vectors being added by the oscillation in conjunction with the upstream blades begin to lessen, while the vertical velocities of the downstream blades begin to accelerate, allowing them to have increasing levels of interaction with the medium as they make their smooth transition into additive oscillation mode. What is more, as this part of the cycle is happening, the upstream blades have now become streamlined to the force and velocity vector inputs of the downstream propeller. This concludes this introduction to the technology of oscillating counter-rotation. Any parties interested in either licensing or investing in this technology should direct their inquiries to admin@contrapel.com.